I'm humbled to be here. I greatly appreciate it. Good morning, good afternoon, good evening, depending on where in the world you're tuning in from. Thank you for that wonderful introduction. I'm going to really greatly appreciate that. We are going to just jump and dive right in. Yeah, it might be a mouthful, but it really, if you want to zone in on one word, it's microservices. We're building microservices, and we're using Cosmos DB and specifically its change feed to build those microservices. And this is somewhat, of course, we want to give special thanks to Microsoft and all of our supporters. It's really important to keep these events going. And I'm, again, really thrilled to be here. And thanks to for all the support that we're getting for the conference. Our objectives, yes, it is somewhat of an advanced session, but I am in no way assuming that you actually really have a great knowledge of Cosmos DB or much of any knowledge, because we are going to review the most important aspect of Cosmos DB, which is partitioning. In a word, partitioning is the most important aspect of Cosmos DB. There are many other aspects, of course, but partitioning is core. So we'll review those concepts, and then we'll look at the change feed and see how partitioning affects the change feed, and how that understanding will enable us to build those microservices. And these will be event-driven microservices because they are going to be driven off the events coming out of the change feed. So let's start with the change feed. In Cosmos DB, we store data in containers. And every time you store a data in a container or update a data in a container, that change gets emitted through the change feed. And that opens up a wide range of possibilities, including replication. I'll talk about what I mean by that, because Cosmos DB internally has replication for failover. That's not the type of replication we're talking about here. We're talking about a business applied use of replication, as well as denormalization. These are important concepts when data modeling in Cosmos DB. How you might generate notifications when any event of interest occurs through a change in a Cosmos DB container. You can trigger off those notifications. Very important, critical aspect of Cosmos DB when you're building large-scale applications. Materialized views, we'll talk about those, we'll see what those are, and data movement, because of course any data that gets moved into Cosmos DB that then gets emitted through the change feed could then certainly be moved downstream to some other system as well through the change feed. And all of these could be wrapped up as microservices, and I'm just going to define microservices very loosely as, these are very small, hence microservices, single responsibility, single purpose, ideally self-contained, and most ideally not dependent on other microservices. So the Cosmos DB change feed gives you this kind of central event source where you can have independent microservices that do not rely on one another, consume the change feed even at different paces, and track their state as they consume the change feed. Right? I'm going to cover all of these scenarios today. The last three of which are, I'm going to have some really juicy demos. The second half of the session, we'll have some really juicy IoT demos for notification, materialized views, and data movement. But first, like I promised, we're going to start off with covering these core concepts that are critical to understanding Cosmos DB and how you can effectively build these microservices. Partitioning, or horizontal partitioning, if you will. Yes, we view a container as a single logical resource that we read and write documents to and from, but of course, under the covers, Cosmos DB is maintaining a cluster, right? There are a number of physical machines, physical servers, if you will, or let's call them physical partitions, which are almost like physical machines. They will also replicate internally. So they're also units of replication. But for our intents and purposes, think of it as just like a box, like any other box. And the more data and throughput required for a container, the more boxes we throw at it. And there's really no upper limit to the number of boxes or physical partitions in the cluster. And again, thinking of each one as a machine, each one gets its own storage, each one gets its own CPU, and hence this design will give you unlimited storage and unlimited throughput if you partition your data properly. Okay. So I mentioned the word physical partitions. Now let's talk about logical partitions, because that's really what we need to concern ourselves with. Cosmos DB manages the physical partitions, we are in control only of the logical partitions. So let's kind of zoom in on 3 of these physical partitions and imagine we are throwing documents into the container and they are of course landing on these various physical partitions. That how does Cosmos DB know which physical partition to store which document? The answer to that of course is logical partitions, which we define. So a logical partition will never ever span physical partitions. This is a blown up diagram. You wouldn't normally have an entire logical partition in one physical partition, but I'm just showing the breakup here, right? And when you create a container, you define that partition. So if we shift this to some sort of, let's say, social networking scenario, where you would choose, let's say, the username, right? Let me see if I can get my laser pointer working. Oops. Yeah, that works. The username isn't going to be my partition key. That is some property in my data. But every document of every type will always have a username property, and that's what we're going to use to partition all of these documents. And that would mean, again, in a social networking scenario, all of Tim's documents would be in one logical partition, all of Andrew's would be in another, and so on. And these, again, would be documents of different types because it's schema-free. Every JSON document has its own shape. So this first document might be the user profile for Tim, and then the next several of those documents in the same logical partition could be posts of Tim's. So they're documents of type post, because they are posts that Tim has created. Maybe some of them are of type comment, because Tim has commented on somebody else's post. Some of them might be of type like, because Tim has liked another post. So I have these documents of all these different types, right? It was just common NoSQL, right? Schema free. But one thing they all share in common is that username partition key property, and that's what lumps them all together in a single logical partition. And that would mean that you could retrieve all of Tim's posts in a single logical partition, or a subset of those, right? So you can filter down on a logical partition. Obviously, it would still stay constrained to that one logical partition, and would therefore be very efficient. Okay. So let's talk about some common partitioning patterns, because here I just talked about using the username as the partition key. So understanding Cosmos DB, there is a property called ID, and in Cosmos DB, every document in a container is unique within that entire container based on a composite that is a combination of this ID property and whatever property you also choose as the partition key, let's say username. But if you actually choose the ID property itself as the partition key, which might seem odd thing to do, you wind up with exactly one document per logical partition. You will never get more than one document in a logical partition. And that doesn't seem very efficient, certainly from a querying perspective. But actually, if your most common querying pattern is to query single documents, let's say a point reads, and or update single documents, like ingesting massive amounts of sensor data and telemetry data in IoT scenarios or retail scenarios, for example, then this actually is not only a common pattern, it is the recommended pattern. It will give you the most, the greatest scale. It'll give you the most, the greatest partitioning, and will span out your container as needed as you ingest that telemetry data. But of course, if you want to query for multiple documents, it doesn't seem like a very efficient pattern. Another common property you might use is a type property. Sometimes you need to store small amounts of data in Cosmos DB alongside the gargantuan containers of data, like lookup lists. Like if you were running an airport, obviously all of that IoT telemetry would be huge amounts of data, but your small lists of flights, the airports that you service, in an e-commerce scenario, your list of product categories, and what application doesn't have a list of states and provinces, right? These types of scenarios, it's very common to say that the amount of data is small enough to fit reasonably within a logical partition, which is, I believe, 20 gigabytes at this stage. So, you never get 20 gigabytes, a list of states and provinces that comes anywhere near that. And airports as well, and the flights and so on that you operate out of your airport, right? So for that, you would kind of lump them all together. All of the documents of type flight would have a type property whose value is set to flight. All documents of type airport would have a type property whose value is set to airport, and that's what would kind of like lump them all together. And then you could very efficiently return the entire lookup list, right? Because it's all in one logical partition. If it's all in one logical partition, then it's all in one physical partition, and then Cosmos DB can most efficiently wrap your query. Other patterns, there are numerous. We're not going to go into all of them, and they're going to depend on your most common querying patterns. You're going to want to satisfy your most common querying patterns. For an example, I mean, I gave an example already with the username in a social networking scenario. In an e-commerce scenario, it might be customer ID, where again, within the same logical partition, you have documents of different types. You'll have a document of type customer, and then you'll have a document of completely different schema of type order. And they would live in the same logical partition, which would kind of, I hate to use the word joins them together because we have no joins in Cosmos DB, but essentially it fills the gap that you get when you don't have joins, in the sense that you can efficiently return the customer with their orders, right, from Cosmos DB in a single logical partition. So let's take a quick time check here. I think we're doing good on time. Order and change events. Now, one of the beauties of the change feed is that it not only serves as a persistent log of events of all the inserts and updates since essentially the beginning of time when you created the container. It preserves the order, and that is quite a challenge when you consider the scale and the way that Cosmos DB splits physical partitions behind the scenes as your data grows, and it still has managed to maintain the order of those events. Let's see how that's achieved. Let's look at an e-commerce scenario where you're modeling your data as events. So there are only inserts. You are never updating or deleting data, because everything that occurs is an event that gets inserted. So when the cart gets created, when an item gets added, when the user removes a cart, that's a new event that gets inserted, rather than removing a document from the container, right? So modeling as events, right? It's clearly critical if you have multiple microservices that are watching it for these events and taking off. Let's say a microservice is doing tax calculation, another microservice handling fulfillment or delivery, that sort of thing. And they're all running independently. It's critical that they process these events in this order, all right? Because indeed, by the time the cart is checked out, item 2 has been modified and item 1 has been removed, right? So you can't add it after you remove it. So how does this work in high volume and high scale? Let's look at our physical partitions. And again, just like a container is a single logical resource behind which you have multiple physical partitions, that change feed is really an abstraction, because each physical partition really has its own change feed behind the scenes. And if you want to get down to the low level, and in the early days of Cosmos and the change feed, this was really the only way to do it. You yourself would, have to discover the physical partitions and parallelize the workload across them and consume their changes, which is, not pleasant and lots of housekeeping work to be done. But fortunately, today we have the CFP library, the change feed processor library, which you'll see makes that much easier. But if you just get down to the low level, what happens here is that if the user starts a cart and that lands on one physical partition, and another user starts another cart and lands on another physical partition, at the point in time that the item is inserted into the physical partition, it is also stored and emitted through the change feed of that physical partition. So even if user B adds their new item before user A and so on, and this kind of fills out this way, you'll see that within each physical partition, the events are stored in the order of logical partition. So that's why this is really critical to understand. When you're picking your partition key, you are also determining the order of events. And it doesn't matter that carts A and C are interleaved and that carts B and D are interleaved. Within cart A and within each individual cart, the events are in sequence. And what happens at some point in time is that Cosmos DB is going to split a physical partition, because it has become too full, either data or throughput or both, depending on the throughput that you've provisioned. Cosmos DB will determine it needs more processing power and will spin up a physical partition and will essentially split one of the other physical partitions without disturbing the others. So, and by doing so, it'll remove, and of course, this new physical partition gets its own change feed, and it will move roughly half of the logical partitions over. I have limited space on the PowerPoint here, but it would have moved many logical partitions, roughly half, over from physical partition 2, which is being split, into the new physical partition 3, and simultaneously move the events over, preserving their order, all the events for all of the logical partitions that were just moved. And then things go along their merry way, right? But and then further splits can occur. But again, if you look at, if you ignore the interleaving, you will see that within each logical partition, the events are preserved in sequence. So this is a guarantee that you get, even if you need to, I don't know, one microservice fails and needs to be restarted or rewound to the previous hour or day or week, whatever it is. It will always be able to reprocess those events in the order that they occurred. And that's really important for disaster recovery. So again, if you just follow the events on each individual partition, you'll see that they are in sequence of a logical partition. But of course, we don't have to concern ourselves with the physical partitions. We are going to get to look at one logical change feed, because as I started mentioning, the change feed processor library is going to handle the work of parallelizing the consumption of the change feed data from each physical partition and hand you one logical change feed. And because that's being parallelized now as well, so things are very interleaved, but you get one change feed, and if you go through it, it doesn't matter that it's A, D, C, etc. All of the individual cards events are being processed in sequence. This is kind of a really critical point in Cosmos DB. So how do you consume the change feed? I mentioned the directly is undesirable. It was originally the only way. You had to discover the partitions. You don't want to do that. You want to use the change feed processor library, which you're going to see in action soon enough. And it is both stateful and scalable. What do I mean by that? It's stateful as in there's a special container that it creates called a lease container. It's a very small, inexpensive container. It's a little cheap container there that just manages the state, and it keeps track for each physical partition when the last read was, so that as it pulls in the push model, or because it's a push model and a pull model, but we're focusing on the push model, as it pulls, it can keep track of where each partition was last consumed, and you don't have to concern yourself with that. And it is also scalable in the sense that it will parallelize the workload across multiple partitions. So you get those benefits without you having to do that work yourself. And the easiest way, or one of the easiest ways to wrap yourself, to deploy something to the cloud around the CFP library, is to use an Azure function. It's a serverless wrap around the CFP library. There are, of course, other options where you have more control over the deployment. But for Azure functions, that's the way we're going to go for the demo today. You'll see how it's quick and simple to get this up and running. All right, that is about the end of our kind of like a general overview of partitioning and what you really need to understand in terms of how Cosmos DB operates behind the scenes in order to now address the various scenarios that I started listing. It was like replication, denormalization, notifications, materialized views, and ending things off with the data movement. So starting with replication, you have to choose a partition key, as we've discussed, and you will base it on what your most common querying pattern is. We saw examples of that, talked about examples of that. But the thing is, you can only choose one and only one. This is kind of like a physical hard limit. Although there's a new feature coming out soon called subpartitioning, which is an interesting twist on this. But for all intents and purposes, and certainly today, you can only choose one partition key. But what if you have really more than one common querying pattern? Because these cross-partition queries, where if you have to query across logical partitions, they're not necessarily evil if they don't occur most of the time. They're only a problem if you're hammering away high volume and high scale with cross-partition queries. That you need to avoid. And what if it's like really 50-50, which can happen? And in that scenario, you can create a replication microservice that is whose sole purpose in life is to keep two containers in sync with one another in terms of their data, but each one is partitioned differently, and therefore each one is suitable for one type of querying pattern or the other, for example. Let's go back to an e-commerce scenario, but now we're going with a stateful model, like a kind of like a relational model, if you will. We have true inserts, updates, and deletes. So I have a document that's stateful. It looks like this, and it shows, an item in a cart. And I partition this cart on the cart ID. So if I run a query like so, to get all the items in that one cart, I will get all the items very efficiently, no matter how many there are. And I can, of course, filter, like only give me items in the cart with quantity greater than 0, or manufacturer, or only the Surface Pros in this case, right? From a given cart, right? It's going to be very efficient. So cart ID is a good candidate if that's my most common query, because the partition key is known. And if the partition key is known, the query can be routed to a single logical and hence physical partition. But what if I need to get all the Surface Pros? Like across all the carts, but just the Surface Pros. And then maybe further filtered on Surface Pro by carts that have more than 10 Surface Pros, right? Something like that. But like where I know the item, but not the ID. That is a cross-partition query, which again, if occurs here and there, is fine. But if it is a very, very heavily utilized query, then it will become expensive and actually become more cost effective to implement a microservice that actually listens to the change feed on the cart container, replicates the data over to another container called cart by item, which is partitioned on that item property, but essentially holds it just a copy of the data, right? But now the partition key is the item. So that second query can be satisfied by the cart by item container. And the job that for our microservice is just to make sure that they are in sync. And that's a very easy job. By the way, all of the source code, so I'm going to be showing demos for the last 3 out of the 5 of these scenarios, but the code that accompanies the session has code for all 5 of these. So let's talk quickly about processing updates and deletes. To date, at this current point in time, intermediate updates are not recorded to the change feeds. If you update a document more than once, if you insert a document and update it 4 times, you only have one version of the document, which is the most current version of the document in the change feed. If you rewind the change feed, you're not going to get those interim updates, okay? So, right, for an event-driven model where everything's an insert, that's not an issue. But for a stateful model like our shopping cart example here, that could be an issue. For replication, it's not, because if we ever had to blow away our replica container and rebuild it from scratch by rewinding the source container to the beginning of time, we really only need or care about the latest version of the data, because that's the most up-to-date version, and that's the one that's going to wind up in the replica. So it's fine. But deletes are actually a problem, because deletes as well are not written to the change feed. So this could be a problem for our synchronization, because we don't want orphans, right? In a situation like this, where the quantity changes on the left from 2 to 3, like so, it's easy enough to pick up that change and have your microservice update that document on the right-hand side. It's certainly straightforward. And the same thing, if it updates to 4 on the left, it can get updated to 4 on the right. But what if this document is being deleted? You cannot simply delete it from the cart on the left, because if you do, it will not be picked up by the change feed, and it will remain in the cart on the right, and you will have orphan documents, which of course you do not want. So the solution here is to use a TTL, time to live property. This is a special property. You're not free to use that property name for yourself, because if it's there, it means that there's an expiration on this document. Cosmos DB will expire this document automatically, giving you 60 seconds to pick it up. And when your microservice sees the TTL property on the left, it will actually delete the document on the right. Now, 60 seconds is way more than you need, because the change feed is being processed in the push model in near real time. It's like almost real time. Like usually when things are caught up, it's in, we're talking about several milliseconds. But what if the microservice is down and what have you, or you need to pause it and restart it? You could even give it a little more time if you want, but within 60 seconds later, the document will be gone from the container on the left as well. Now, here's something that's breaking news. There is a private preview, anyone who's interested could let me know if they want the link, because it's not that private, I don't think. But it's not even in public preview yet, so it's still not going to be, I don't think, at least the end of the year, quite honestly, probably not until the beginning of next year at the earliest, but I don't know that for sure. And some of these terms may change, but there is a feature called the full fidelity change feed. That name subject to change, of course, but the idea is that you do get this operation log here on the right. So this item log here is the way things are today, right? Only the inserts and the latest updates only. No deletes, and no previous versions, but the retention is infinite. But there's no additional metadata. You can't look at a document until if it was an insert or an update yourself. But the new operation log will have every insert, every update, every delete limited for 30 days. So if you need some sort of disaster recovery, you cover it for about 30 days there. And you can inspect metadata. You will be able to inspect metadata to see whether it was an insert, update, or delete. And even if it was an update, you can get access to the previous version. And you can tell if it's being deleted as a real delete or by using that TTL trick. Okay. Next scenario was denormalization. So for handling denormalization, Cosmos DB is, of course, non-relational. There are no joins. There are no relational constraints. And that's really a big paradigm shift for a lot of us who have been working with relational systems for many, many years. So it goes against the grain of a lot of our best practices, and things that were best practices no longer are, and like there are actually anti-patterns that we implement, and one of those is denormalization, where rather than striving to normalize, we actually, I wouldn't say strive to denormalize, but we pick and choose certain data points to denormalize based on our querying patterns, like things that we need to have readily available. And especially if they're not going to live in the same logical partition. Let's try to duplicate that data so we don't have to visit. It's like I guess the best analogy I can give for a SQL Server person is like a covering index, where the index includes copies of the data from the main table, right? And so you don't have to make that extra key lookup. So let's talk about querying products, for example. If I've got a product document that looks like so, there are several IDs in here. There's the ID, which is the product ID itself, and there's the category ID, and then there's this array of tag IDs, but there are no names because the names live in our metadata. We have a metadata container where we store that master data, if you will, like every category's name and every category's category name and tag name. And just the IDs are stored in the product. So that results in very expensive queries like so. You have to run this first one to get all the products, the second one to get the category name, and the third one iteratively on each category to get all the tag names for all the tag IDs in that array. And that's like, clearly undesirable, extremely expensive. And we wouldn't think about this in the relational world because we just do the joins to get that information, but we can't do the joins here. So the answer is, again, to denormalize, and that is to say to store a copy of that master data. So now in addition to the category ID, I've got a copy of the category name. And that tags array is no longer just an array of IDs, but it's an object array that has an ID and a copy of the tag name. So at the point of insert, I'm duplicating the data. At the point of insert, when I'm creating a product document, I'm copying the current category name and tag names based on the current IDs. And that's all fine and good. But of course, what happens if there's a change, right? If somebody changes the master data, like the category name changes, and you need it to be reflected in all of those copies, if you will. So the answer to that is, again, through a microservice. So here in this scenario, I've got my metadata on the left. And anytime there's a change to the master data, let's say category CH, whose name is shorts, whose value is duplicated here and in potentially many other documents. If somebody goes in and changes shorts to fun shorts, the microservice will wake up, query for all of the matching documents on the right, and actually apply that change. Or if somebody changes the tag name outdoor, TOD, from outdoor to outdoors, they pluralize it, same concept. You'll see that the microservice wakes up and cascades that change across all the related documents, and multiple documents on the right-hand side that are impacted. And that's how you keep the category names and the tag names in the product document. So when you retrieve a product document, you have everything you need to, let's say, display it on a web page without having to do that extra lookup for the category name and the tag names. All right, now is where the fun begins. If you're still with me, I hope that you are. I hope you're enjoying the session so far. Now is where the cool demos begin. So we're a small airline. We operate only 12 flights across 6 airports, but we have certain requirements. We need real-time flight information, obviously, but we also have no-fly zones, and we have to be alerted to if a plane enters. We need up-to-date arrival information to display on arrival boards in the airport, or for just client applications that are consuming this information. And we need a way to permanently archive the data. So we're going to ingest this IoT data into Cosmos DB where we need it for the short term. But for the long term, it's not cost effective to store it permanently. The value of this data is all very current, right? Like the current flight information is all real-time information. We keep it around for 30 days, so we can run our reports. Maybe we keep it around for 60 days, but at some point, it's not really limited value, but we don't want to discard the information. So we're going to build microservices. Once we ingest all that flight telemetry, we're going to build microservices to generate email alerts if you enter a no-fly zone, to build materialized views to give us efficient real-time information and arrival information. And we will archive to blob storage so that we can permanently archive data that we don't want to lose, but we no longer need to keep in Cosmos DB. So remember we talked about the various different patterns, partitioning patterns, and I mentioned that the ID property itself is suitable for IoT telemetry. So that's what our location container is going to use. So see, our location container is going to ingest the flight telemetry. This will be all the information about the current point in time of every flight's speed, altitude, duration, location, etc. And we're ingesting at a very rapid rate, every 10 milliseconds per flight. So we are going to partition this container on the ID property. Remember, that will give us one document per logical partition, not terribly efficient for querying unless you're doing a point read on a document, which is kind of difficult if the ID is a GUID, which it is. So, but it is optimized for bulk ingesting, right? And so that's why we're going with the ID property. So let's jump into some demos. I'm going to just do a quick check of the slides. Okay, great. So some of these I'm going to go ahead on in the demo, and then I'll just do a quick review on the slides. So let me jump in here to the Azure portal where you can look at our Contoso Airlines database. We've got several containers. The only one that has data in it at this time is the location container. The rest of them are all empty, reset in advance of the demo for this demo. But the location container, if we click on the items container, and you can see this is showing us the ID property and the partition key. And since the partition key is the ID property, that value seems to be duplicated. And there's the ID. And we have many documents of this type. How many? Let's do a count query. All right. We have 3.2 million. It's not actually a gargantuan amount, but it's substantial enough for the demo, right? I'm sorry, 32 million, which is also still not a gargantuan amount in terms of big data. But for our demos, that's 32 million documents. It's a fairly sizable container. All of the other containers are empty, except the meta container, because it has our metadata. That's the one that, remember, I told you the proper partition key to use is the type property. So all documents of the same type are kind of lumped together in the same lookup list. And we have two lookup lists. We have a list of airports. You see there's 6 of them. And we have a list of 12 flights that operate between those 6 airports. And here's what those documents look like. Each airport, its location and its name, and each flight's departure and arrival. This is all metadata, small amounts of metadata. We have a gargantuan we will have gargantuan amounts of data in the location container, 32 million documents already. And you can see, again, we have partitioned this location container on the ID property itself. And looking at documents of that type, you see for each flight at this particular point in time, this is a timestamp here. It can be translated into a timestamp. At that particular point in time, this document was emitted by the aircraft to indicate, well, there's some static information about the flight in general, but then it's current latitude, longitude, altitude, speed, etc. Remaining minutes. The is complete property is kind of going to be important to our application. I've designed this simulation so that when a plane lands, is complete gets set to true, and there's only one document that's going to have is complete set to true. You do not want to miss that event. It's okay to throttle your events because you don't need to process every single one, let's say, as you'll see, but you're not going to want to miss that one. You'll also notice there's a time to live here because after 30 days, which this translates to in seconds, I won't need this document anymore. And you're going to see a microservice that I have that is going to archive all of this stuff to cheaper blob storage after 30 days and let my Cosmos DB just get rid of it. All right. That's enough for the containers. And the lease container is empty. The lease container is what's used by Cosmos DB for tracking state. That's that like kind of small container I was telling you about. I will have a look at that at the end. And the arrivals board and current location containers, they're both empty now because they are materialized views that we're going to cover soon. All right, so what do I have running? Let's kill PowerPoint here. Okay, you see I've got 4 microservices here. There's, and look in yellow, there's the email alert microservice for the notifications. The current location microservice is a materialized view. We have the arrivals board, was another materialized view, and data archival. I also have a very cool looking map here. This is a bit of eye candy that I was having fun with during COVID. And so we can see our list of flights. Those are our 12 flights. And if I click on Washington, DC, you see the red circle here, that's our no-fly zone. So if a plane enters that area, we need to be notified. I'm going to go ahead and kick off my flight telemetry generator, which is right here. I'm going to say generate in continuous mode, which means the moment a plane lands. And let's monitor one flight from JFK to LAX, JFK to Seattle, two westbound flights. And but those are the only 2 that we're monitoring, but we're going to kick off all 12 flights right now. There we go. And off they go. We're airborne. Oh, there's our planes. There's our aircraft. But they seem to be flying a little too close to the no-fly zone for comfort. And there they go, entering the no-fly zone. So I'm going to go ahead and minimize this. Oh, there we go. There's the email alert Microservices. I got to pause it, scroll up. You'll see, there we go. Flight has entered a no-fly zone. Let it keep going. And if I jump on over to my email, I've got 2 emails now. I just got. Just pop one open. Oh, let me pause the flights. There we go. 9:39 a.m. 9:13. That's where I am here in New York City. And here's my email and alerting me because this flight has entered a no-fly zone. I've got another email alert for the other one. And you see that the microservices have paused because the flights, I have the magic ability to suspend my aircraft in midair. So as soon as I resume them, the microservices wake right back up. There we go. And wherever you see yellow output, it means the microservice is doing something. So we're going to have a closer look at the microservices. I'm going to pause that again and flip back on over to the slides. And let's see. So for no-fly zone alerts, we're going to track all flights, just like we saw in the demo, right? I don't have to cover this. We're going to do this by monitoring the change feed. We're going to, obviously, there's some spatial query involved here. Let's have a look at the code. So let's flip on over to Visual Studio. Here are our 4 microservices. Each one of them is an individual Azure Functions project. That way they can be deployed and debugged individually. So even if they were independent of one another, if you lump them all into one project, then you kind of have to deploy them all together, and you really want to keep them separate. So I've got exactly one function for each, and I'm running all 4 of them concurrently because each one's running on its own dedicated port set here in, I think it's this one. I'm not sure. Yeah. No, it's this one then. Local settings JSON. Right. This is on port 7073, and each one of them is on their own other port. So we're looking at the email alert microservice, right? So let's drop in there. Very small amount of code here. This one's running on port 7071, and it's got a bit more configuration information than the other microservice did. So let's look at the code and see, and then we'll look at this configuration info and see what's going on. Make that nice and large for you. One more. That's the way. All right, so we'll get into these private statics in a moment. Let's just zone in on this public static function here, which is called email alert, but the actual name of the Azure function is email alert because of this function name attribute. That's the publicly advertised name of this Azure function. It's called email alert. And you can see that the parameter signature itself has an attribute called Cosmos DB trigger, because Azure functions are tied to triggers of all different types. You can have a trigger that fires when someone drops a document in blob storage, right? Excuse me, a blob storage trigger. In this case, a Cosmos DB trigger specifically means something that triggers in response to the change feed specifically. And I've got constants because I'm a good boy. So you see, if you look at the IntelliSense, you can see that the string constant name here, it is our database, Contoso Airlines, and the collection name, which unfortunately is the old name for container, but you still see the old name used. Collection, container, they mean the same thing, but we try to use the word container unless we're going with MongoDB. MongoDB calls it a collection. And look at the container name, it's location, our location container. Basically, watch the change feed on this location container, which you can get to by connecting to with this connection string, which we saw in local settings. And there's my super private account key. That allows you to connect, sorry. And the name of the lease container to use, and you'll see that all of our microservices point to the same lease container, but they each have a unique lease container prefix that I always set to match the name of the Azure function, so that you'll see that they can independently preserve the state of where they're up to. Like if one of the microservices gets paused or goes down and then comes back up, it's quite a bit behind the others. But you'll see how it tracks its own state. But this is all metadata. In terms of the actual parameters that are handed to your Azure function, it's only these 2, which are the only 2 that you need. You are essentially handed a read-only list of documents that have changed, that you can now process, and a logger for you to write output. But remember, this is being fed to you by an Azure function that is wrapping the CFP library that behind the scenes is parallelizing the workload. And there will be multiple instances of your code. Oh, what happened here? Okay, what's going on? Come on, Visual Studio, do this now. Anyway, Visual Studio is being funky. Okay, thank you. This code all has to be thread safe because it's being parallelized, and you'll see that's come into play in a moment. I keep a nice short for each here where I process each document by checking the location and passing in the document to be checked. Now, if you check the flight location, you can see I'm getting a document that is just an Azure document. That is just an Azure Cosmos DB, an Azure Documents document. It just represents a generic JSON document, but I can deserialize it to a strongly typed class that I have here called location event, which exactly matches the documents that you saw in the portal, those location documents, except of course for the camel case to Pascal case conversions that are common with JSON and C#. They are essentially that location document. I get to inspect each location document. And I call my business logic spatial no-fly zone. So spatial up here is my little business logic that performs the spatial calculation. Is it in the no-fly zone? Very simple logic. For the demo, we're allowing 150-mile radius around the coordinates for Washington, D.C. Let's calculate distance does the job. It's just, obviously you have a whole bunch of no-fly zone rules that you would retrieve from a database. They would involve polygons and overlap intersection queries. But for our demo, it's good enough to say if you were within 150 miles of Washington, D.C., you're in a no-fly zone. Now, if you're not in a no-fly zone, we let the event fly by, no pun intended. Like the event just comes and goes. Like first of all, this microservice is not storing any data. It's just watching events. And if it's not in the no-fly zone, it does nothing with it. If it is in the no-fly zone, it needs to trigger an event, an alert, but we want throttling logic because we don't want an email every 10 milliseconds. Certainly not. This logic here ensures that you don't flood an inbox, which would be quite absurd. You need to basically say, and in this case, I'm saying every minute that a plane remains in a, you'll get an alert the moment you enter the no-fly zone, and as long as you remain within the no-fly zone, every minute thereafter, by doing this simple date time. But this thread lock here is just my basic way of being thread safe between the point in time that I check if the dictionary contains a key and the point in time that I actually add it if it doesn't exist, or update it if it does, that another thread doesn't come along and also add it. And I've got two at the same key and it blows up, right? You know what I'm talking about if you've done any thread safe coding before. And then, of course, I want to send the email after tracking in the dictionary for each flight when I sent the email last, so that it only occurs once a minute if they remain in the fly zone. Send email itself, this is for a demo, so I'm actually delivering the email from the microservice. Again, defining a microservice as being very limited in scope, and especially with an Azure function, processing high volume of events, you don't want to throw exceptions. So the more you do, the more chance there's to throw an exception. I don't care how good of a coder you are. I have introduced the potential for many exceptions to occur by actually delivering the email, where the job of the microservice is really to detect if a plane has entered the no-fly zone and let's say queue a notification for some other service to pick up that from the queue and deliver it accordingly. I mean, it might not be email, it might be SMS, it might be based on notification preferences. There could be all sorts of complexity in that does not belong in the microservice. But for demo purposes, I'm formatting a nice little email in HTML, in an HTML table, like you saw, like I showed here. You saw the email already. And I'm using SendGrid, which is just a very super easy way to send emails on Azure, but it could be SMTP. That's what the SendGrid stuff here is. And that's it. I don't think there's much more else to cover in the email alert function. Not at all, right? Because all of this other, yeah, we covered the thread locks and the timestamps for throttling, the stuff that comes from config for, using SendGrid to deliver the email, and our business logic, and there's our function, and that's the code. So I'm not going to spend any more time on that. I'm going to jump on into the next piece that I want to cover. So that's a cool map, right? Watching the planes fly. How did I do that? Well, how did I know what the current location of each plane was in order to draw them on the map? And the answer to that is I queried the location container using a query like this. But this is very expensive. But it allows us to render a map. But think about how expensive this is. I'm querying a container that currently has 38 million, but it could be 38 billion or 38 trillion documents in that container. And I'm only really ever interested at any given point in time in 12 of those documents. 12, the 12 most current. So I'm querying through all that amount of data at high volume and high velocity is extremely expensive. But it works, as you saw. I'm going to go back to the demo here. I'm going to go back to my flight telemetry generator where my planes are suspended. I'm going to resume them flying. You'll see it's working, right? The planes are moving, the planes are flying. But if we go look at the cost of these queries, I'll clear it out, start over. Look at each time I query, I'm only querying for 2 flights every 3 seconds to keep my flight updated, my map updated every 3 seconds. I'm querying 2 flights. Each flight is costing 71 RUs. Now, I know you might not know what that means. RUs are request units, and you might not know if that's expensive or not. So let me tell you, that is very expensive, and it will only be more expensive if they were not 38 million documents, but 38 billion or trillion. This is not what you want to do, because you're really only ever interested. Let's just go ahead and make this really insane and track all 12 flights. So now every 3 seconds, it's 71 RUs times 12. And you can see it rack up there very rapidly. I'm already at 3,500 RUs, almost 4,500, and so on. And this is prohibitively expensive. But there's the top one query, because all I know is the flight number. I'm ordering by timestamp descending, so that I get the latest one at the top, and I select top one, and that's how I get my map. But it's really not very efficient now, is it? This is actually prohibitively expensive. So let's pause flights. So what we want to do is use a materialized view. And this is actually, I'm going to show you 2 materialized views. The first one is super simple. The second one's a little more complex. I'm not going to get into the complexity of it, because it's the concept that you have to latch onto, which is you capture the information that you need to present once, and you store it somewhere, and then it could be queried very inexpensively and cheaply from that location compared to the source location repetitively. So we saw how expensive it was for running that top one query over that large amount of data. We're going to build a materialized view. We're going to build a container that's only ever going to have 12 documents in it, 1 document per flight. We're going to, and the partition key is going to be type, because they'll all fit in one partition. And I will set the ID to the flight number. I'll change it from the GUID, which is a meaningless value, to the flight number, which is a meaningful value. And now I can do those point read operations, like the super efficient single read, single write operations when you know the ID and the partition key. And that will make it extremely cheap to get the same information. Granted, it will be lagging slightly behind. But now when I flip back on over here and I can resume my flights in the air, I check this checkbox, use materialized view up here. Well, you can see that I'm still watching flights in real time. They're flying. I'm going to clear them all. I'm going to start with 1 flight. Oh, he's almost landed, but he's going to take off as soon as he lands. There we go, because I'm running in continuous mode. And he's flying along, and I'm watching him fly, but look at the logs. What's the cost? 1 RU, and it does not get any cheaper than that, because I'm doing a point read. I'll show you the code real quick. First, let me show you the container. Just flip back on over to the portal. Where are you? There you are. Let me pause this. And if I look at my current location container and I look at items, there's only 12 documents in there, and they all have the same property. They're all this is a partition on the type property, and they're all set to location. So I know the type property of every document's location. I can get all 12 at once very efficiently, or I can get each one individually very efficiently, because the ID is no longer a GUID. The ID is actually the flight number. I copied it over in the microservice. I'll show you the code right now. So let's see the code for that microservice. Sorry, just fighting with the mouse. There we go. All right, that is the current location microservice. You're going to see a super similar pattern with our Cosmos DB trigger. It is watching the location container, the same location container as the other microservice. It is using the same least collection, but it has a unique prefix, so it maintains its own state. And for each one, I just update the current location. I told you it's super simple. Okay. I do the same deserialization as before. I deserialize the document. I check if I should skip it, because I also want to throttle this. I do not need to update the current location container every 10 milliseconds per flight. I can do it every 3 seconds. So I call should skip, and you'll see it has that throttling logic. And we'll look at the throttling logic in a moment, but you'll see that the actual logic when you shouldn't skip the event is super simple. I said you take that GUID that's in the ID and you replace it with the flight number. and then you upsert the item, which guess what? That does an insert or an update, depending on whether it's there or not. Writing to this container, which is not the location container, but the current location container. You see, that's the one being passed in. And see my IntelliSense, that's the current location container is my target container. My source container is the large location container, right? The regular location container, and it essentially upserts those documents. They'll only ever be 12 at a time. So it should skip. So I can skip every 3 seconds. But remember what I told you about that all critical is complete event? I never want to miss that event. That event should never be missed. I don't want to miss it because I'm throttling and like skipping events every 3 seconds. Only those that occur every 3 seconds. If there's an is complete event that occurs within those 3 seconds, it will still be processed. It will not be skipped. And that's it for the current location microservice. And I'm not going to get into the details of the complexity of the next microservice that I have, which is the arrivals board microservice, because again, you need to get this. You need to take the information about the current flights and group them by airport in order to give you a nice, let's say, a document that looks like this, that shows that arriving at LAX are these 4 flights with these remaining minutes. I mean, converting the large amount of data into these simple documents where I'm not going to have more than 6, or 4, how many airports I have. It's better to have the microservice do that. And it does that in memory. I'm going to show it to you real quick. First, let's run the demo. Let me continue and flip on over to. Oh, wait, I have something very important to show you on the previous microservice. If I go to my location map, where I'm monitoring 1 flight that's in the air, it is costing me 1 RU. See, every 3 seconds. I run this every 3 seconds. It's costing me 1 RU every 3 seconds. Let me go back to the location map and query for 2 flights. So clearly that's going to be 2 RUs now every 3 seconds. It's going from 2 to 4 to 6. If I go to 3, you guessed it, it's now 3 RUs every 3 seconds. So it goes from 3 to 6 to 9 to 12. So that tells you that if I add a 4th one, that's going to be 4 RUs every 3 seconds. But watch, I hit the 4th one, look at the logs. I am now no longer doing a point read because my code understands, the way I wrote it, that there's a point of diminishing returns where it's more efficient for me to run a query, a single partition query against the current location container, only 3.35 RUs for 4 flights using in, because they're all in, they're all in that one very lightweight container. But even getting all 12 is going to be super cheap. So instead of doing point reads, where if I do it all 12 would be 12 RUs every 3 seconds, it's only 4.47 RUs every 3 seconds. And if you take away the materialized view altogether, just to remind you again of how painfully expensive, or I would say prohibitively expensive this would be otherwise, there you go. Now we're not using the materialized view anymore. We're back to the top 1 queries and we're racking up those RUs. The arrivals board is very similar. I go to the arrivals board and say that I want to see all of the, flights arriving at JFK. This is JFK's arrival board. You see, it goes down rapidly because my planes fly faster than any's in the world. So it keeps arriving sooner and sooner because my planes fly so fast. But this is real-time arrival information. Here's LAX and JFK. And how it's doing that so inexpensively. If you look at the logs, each airport is a cost of 1 RU and only 1 RU. Again, for the same reason, because my materialized view has generated these documents in the arrivals board container, very few of them, and it's constantly updating them as the planes are flying to produce these documents that could be queried very inexpensively because it's just a straight dump, right? It's just a pull of this data. But it's constantly being updated. Here's the code to do it without getting into too much detail. The arrivals board and I really will not get into too much detail, but you can get the gist of it in the sense that I've got an in-memory arrivals board that's keyed by airport and all the arrivals coming into that airport. And there's a deserialization like you saw in every other case. Whether I always want to include, never want to miss is complete again. And it upserts the item again. But the actual logic to update the board is a bit complex because it's doing, the grouping and, it's not that much though. It's still not that much. It's still, the whole thing is only on, 140 lines of code. It's not that much, but it is basically, maintaining based on that in-memory dictionary of the board. It is upserting to the materialized view. And we can say that arrivals board don't need to be more up to date than every 5 seconds. So again, using a similar throttling logic and similar thread safety logic as I've been showing you until now, able to throttle the arrivals, materialized view, not to be, because otherwise then the microservice becomes too expensive needlessly. I mean, you don't need every 10 milliseconds up. You don't need that arrivals board up to date every 10 milliseconds. Every 5 seconds is more than adequate. Getting running up on close to the end of the demo, the end of the session rather. So let me see what I've got left to show you. Data movement. This is our last microservice, and that is we are not going to, you saw the TTL property, right? That expires this data after 30 days. And after that, we don't want to lose it. Now, we have similar throttling logic. Again, we do not need to store in blob storage every single event that occurred every 10 milliseconds on every flight. That is, let's say, beyond necessary, even unnecessary according to regulatory compliance with federal laws, if there are any, that sort of thing. It's like, it's sufficient enough to throttle. I think I'm got it. Let's have a look at the microservice. Because I actually meant to show you at the beginning of the session that I had an empty blob store container. But you'll see from the file name that these have been created just now. Because our last microservice, the data archival microservice, there's the familiar by now Cosmos DB trigger, watching the location container, calling archive flight location with a should skip method that uses throttling logic to, first of all, ensure you never miss is complete. That event will never get missed. So is completed documents are always going to be archived to blob storage. They'll never be missed. But otherwise, we're only archiving every 15 seconds per flight, and that's more than enough. And it's far less than what we would be pumping into blob storage if we didn't have this throttling logic. Otherwise, it's very small, very simple. And the actual logic to do the archiving, if you've ever written code to write to blob storage, this is going to look familiar to you. You get a reference to the blob, you get the bytes, you upload, and you're done. It's really simple. And then when I flip on over to my blob storage, which was empty, I meant to show you that it was empty when we started, but you can see from the flight history. You can see from the file name, 9:13, 8:35 a.m. That's when I started running the microservices initially, and then it just gets later and later. If I just pick any one of these arbitrarily and have a look at it, come on. Now it's not behaving. I mean, there's more than one way to skin this cat. Oh, is it going to give me a 429? Yeah, I hope not. Flight history. There we go. I just picked anyone arbitrarily. And you see, it's essentially a copy of the document right out of Cosmos, now living in blob storage. Of course, there's the configuration information or the storage can. So all of this stuff in local settings at JSON, when you actually deploy well, first of all, I hope I impressed you by how easy it is and how cool it is to run multiple microservices concurrently with the debugger attached, if you like, in my individual studio. It's pretty awesome. But you will eventually, of course, deploy each of these to Azure. And when you do, these obviously, you can tell from the name of the file, local settings.json is not going to be deployed as well. You'll need to update the settings through the portal or another means on the Azure side so that your function can get this configuration information. And the last little piece to show you before I kind of wind it up and throw it out to Q&A, if you have any, is to look at that lease container. This one here, this tiny little container, which you can see is provisioned $400 use, which is as cheap as it gets. It's like $24 a month. But it maintains the state of all your microservices. If you look at items, you will see I've got several documents here, and and you can see the IDs, and which is the same as the partition key because it's really tiny. And you can see that I've got what appears to be 3 documents per microservice. Why is that? Because in this particular case, with my 38 million documents, I've got 2 physical partitions. Cosmos DB has 2 physical partitions behind this container. And so it needs 1 document for each physical partition. And then it needs 1 document for the microservice itself. So that's 3 in total. So if I start looking at them, I'll go first with the email alert microservice. I'm not sure which one I'm going to get first. Yeah, this is one of the 2 partitions. And then last time that it was queried for changes, so the microservice can keep track of state. But on partition ID number 1, it's a different timestamp. And then there's 1 for the entire microservice. It's just 1 document for the microservice. So that's why there's 3 per. Let me see. I think I'm just about wrapping it up now. We talked about how you can replicate changes to secondary data stores. In our case, for the demo, I fed it into blob storage with throttling, but it can go anywhere. You can go to SQL database or anywhere else. You can use TTL to expire data out of Cosmos DB like we saw, so that it doesn't linger around anymore once you push it into blob storage or a data lake or wherever. So then we saw the demos. And with that, so that was about 1 hour and 8 minutes. To me, it felt like about 20 hours. A lot of content there. I'm going to throw it back to you guys over at DPS and hope that all the rest of you enjoy the summit, and see if we have any Q&A to cover before we wrap it up.
Yes, Lenny, and we have a question, 2 questions, I guess. So the first question is about more like a complaint that Azure Cosmos DB is very expensive in terms of pricing. Any
did I mention I don't work for Microsoft?
Yeah.
That is the most common complaint. Now, here's the thing. There is this perception that's out there, and Microsoft is working hard to turn that perception around. And there's a bit of a misperception these days, especially when there's a free tier, first of all, for low volume, low cost applications, middle tier applications, department level applications. There's actually a free tier. There's also a serverless tier where you pay per request and is very, very inexpensive. And then if you are on the more upper end where you are provisioning throughput on your containers, then if you're doing things the wrong way, I mean, I think I demonstrated with the high consumption of RU charges, right? And I was just 1 client as opposed to hundreds and thousands of clients or millions of clients, right? Of course, how expensive this solution would be if you didn't have that microservice to give you the materialized view, so that you could really scale to that volume of clients without it being crazy expensive. So if you are doing things right and you're still achieving a level of performance that is acceptable, you can achieve cost efficiency. I'm not here to tell you that Cosmos DB is cheap, because that would be absurd. don't know what to say about that beyond the explanation I just gave. But yeah, I understand exactly where that person is coming from. I have the end.
Okay. So another question is about, are there any throughput limits with Cosmos DB?
Actually, no.
Okay.
Although the portal will limit you from some ridiculous amount that is going to give you some ridiculously high charge, only because it's a limit on the portal, because Microsoft would like you to contact them if you throughput limit requirements are that high. To either see if they can help you find ways where you might not need that level of throughput, and depending on your design and architecture, you might be able to get away with less, or B, to maybe cut you special costs, cut you special deals, give you special treatment because you're at that high level. But there is, in theory, like no upper limit because they don't limit the number of physical partitions per container to date.
Perfect, Lenny. And the last question is, I work for a services company in India, a large one, and in my project, I have been asked to explore more about HIPAA compliancy and if Cosmos
More
DB
about
appears.
what compliancy?
HIPAA compliance.
HIPAA compliancy.
Yeah, HIPAA.
Yeah. Sure.
So,
I mean, we're talking. Well, everything's encrypted in Cosmos DB end to end.
Okay.
There's a lot. They've really beefed up security on Cosmos DB since the early days, where it was very low, not very granular. You just basically had users and permissions, and it's not very granular. You can either access a container or not access a container. And now I believe they're integrating Active Directory, and there's also private network, so that the entire Cosmos DB container is not available outside of your virtual private network on Azure. And also everything's encrypted end to end, and most recently they added always encrypted, which is a feature that first showed up in SQL Server, which is the ability for you to have the data encrypted using a key that you possess, and only your clients possess, and Microsoft themselves don't even possess it. So Microsoft can't even access the information in your container.
Perfect. Well, with this, I guess no more questions, Lenny. Thank you so much.
Thank you very much, Amit, and I hope you all enjoyed the session and enjoy the rest of the conference as well.
Absolutely. Thank you, everybody, for joining this session. And thanks, Lenny, for delivering it. Hope you have the rest of the sessions all going today. And, of course, 3 more days to come. So a lot of content there. Enjoy. Have a good day. Thanks, Lenny. Bye.
Thanks. Bye.
Bye.